Welcome to LIB Academy. In this video, we are going to look at what are eigenvalues and eigenfunctions and why do we have to know them. We will also look at a lot of practical problems in order to increase the level of your understanding on this concept. Before we continue, let's look at what are operators and observables. Operators in mathematics are an operator is anything that is telling you to do something. For example, if we have 2 multiplied by 3, our operator here is the multiplication sign. Examples of operators are the partial derivative sign, addition, subtraction. All of these are operators. In quantum mechanics, we have operators in quantum mechanics too. Example of them are p hat as momentum operator. We have h hat as the Hamiltonian operator, which is the total energy of a system. So basically, an operator is a symbol or anything that is telling you to to do something. Observables, on the other hand, are things that we can measure. Example of them are momentum, position, and energy. In classical physics, if you measure the force as force exerted on a substance as the mass of the substance multiplied by its acceleration due to gravity, whatever you get, let's say you get 20 Newton. This 20 Newton is enough to explain the system that we are talking about. The object that we are measuring its force. But it turns out to not be the same in quantum mechanics. So here our observable is the force that we are measuring. Whatever value that we get, we would be able to explain that force when we are looking at classical system. In quantum mechanics, which is at the subatomic level, things are not the same. We are not dealing with the observable straightforward, but we rather have a wave function that contains all the informations we need about the observable. That is why we do have operators for quantum mechanics, which are slightly different from classical mechanics. So now that you know what operators are, observables, and what observables are, let's go back to today's business. So if we have operator and operator A hat operating on a certain function, f of x, to give us a certain constant and that same function back, then we can call this whole term here, we can call this whole equation an eigenvalue equation. Where this one here is the operator, and then C here is the eigenvalue. So since this operator acted on this function to give us a certain constant here, and the same function here again, then this function can be called an eigenfunction. So we would be talking about operators. I mean, we would be using these terms. That is why I initially defined them. So in quantum mechanics, we are dealing with operators because extracting information from a given wave function is not straightforward. So if we have an operator and a given function, and that operator acted on the function to give us the same function back with a constant, then the function here is an eigenfunction. The function is an eigenfunction of the operator A. So the reason why we are studying eigenvalue equations are in quantum mechanics, every single observable in quantum mechanics is going to have a corresponding eigenvalue equation of this format. Let's say we are going to have the operator for an observable, and the observable is what we want to measure, acting on the wave function to give us value of the observable multiplying the wave function again. So if we have an energy operator and we acted on the wave function, we are going to predict the value of the energy and the wave function. I mean, we are going to predict the value of the energy giving us the wave function back. So basically, it's more like if we operate an energy operator on a function, we are going to get the energy value here with the wave function back. Momentum operator on the wave function, we get momentum value here and the wave function. Position operator acting on the wave function, we are going to get the position here and the wave function. That is basically what it means generally. So if we are predicting the energy, total energy of a system, and we act the Hamiltonian operator on this, we are going to get our predicted energy value here plus the wave function back. Mind you, the eigenvalue here is a raw number. It could be 1, it could be 2, it could be 5, etc. But whatever term that we are going to get here should be your eigenvalue. Show that e to the power ax is an eigenfunction on d dx. Solution. You have to show that e to the power ax is an eigenfunction of d dx. Our function here is e to the power ax, and our operator here is, let's say, if operator A is d dx. So the general definition of an eigenfunction is that if the operator A operates on f of x, it should give us the energy value here, I mean the eigenvalue here, plus the function, the initial function. So what is our operator? D dx. So now d dx, and what is f of x here? The function that the operator is acting on, e to the power ax. So e to the power ax. So basically, this operator is telling us that we should find the first derivative of the function with respect to x. So differentiating e to the power ax, what we do is we write the whole thing. e to the power ax. Then after that, we differentiate the power of e. So differentiating ax with respect to x, what do we get? Differentiating x gives us 1. So 1 multiplied by ax to the power of decrease 0. So we are generally going to get a. X to the power 0 is 1. So 1 by a by 1 gives us a. So multiplied by a. So now we now compare to our general equation. Now we have an operator operating on a function e to the power ax. We've gotten a certain value here, a constant a, and the function back. What matters here is after operating on the function, if we have the function back, then this is an eigenvalue equation. Therefore, e to the power ax is an eigenfunction on dx. Is f of x equal sine 2x an eigenfunction on operator b equal second derivative with respect to x? Well, for f of x to be an eigenfunction, if an operator b operate on f of x, we should get a certain constant and f of x back. So now we have operator b to be d squared over dx squared. So d squared over dx squared. And the function here, f of x, is sine 2x. Sine 2x. So now we are going to differentiate this. After that, we compare it to our general equation. So this can also be written as d over dx multiplying d over dx sine 2x. D squared over dx squared means that we are differentiating this function with respect to x twice, and it is the same as writing it this way. And if we differentiate sine, what do you get? If we differentiate sine x, we are going to get cos x. If we differentiate sine 2x, we are going to get cos 2x plus the derivative of whatever is here. So derivative of 2x gives us what? Differentiating x to the power 1. So we multiply this place by 1. So 2 by 1. And the power will decrease by 1, giving us 2 by 1 by x to the power 0, which is the same as 2. So we are going to multiply the derivative of whatever is here by what we got. So now, derivative of sine 2x is going to give us, we have this one here, sine 2x is going to give us the derivative of whatever is here. Derivative of 2x gives us 2 multiplied by cos of whatever is there, cos 2x. Now we now differentiate 2 cos 2x again. So differentiating this, if we differentiate cos, we are going to get sine, right? Differentiating cos will give us negative sine. So we write whatever is here, and then But initially, we will have to multiply the whole thing by the differential of this. So differentiating 2x gives us 2. So multiplied by, let's say we have our 2 there, multiplied by minus 2, then sine of whatever is here, 2x. So simplifying this is going to give us 2 multiplied by minus 2, which is minus 4 sine 2x. So now the whole function here becomes d squared over dx squared, the whole thing, sine 2x equal minus 4 sine 2x. So is this function f of x an eigenfunction? Well, let's see. We have an operator operating on a function sine 2x. By the end of the day, we have sine 2x there and a constant. Yes, f of x is an eigenfunction with an eigenvalue of whatever is here, the constant, which we call minus 4. Show whether the function sine kx is an eigenfunction on the operator d over dx. Now, let's say if this operator is a and the function is f of x, so operator a acting on f of x should give us a certain constant plus f of x again. That is if it is an eigenfunction. Now operator a is d dx, and the function is sine kx. So what do we get if we evaluate this? So if we differentiate sine, we are going to get cos, a positive cos. But before that, we multiply it by the differential of kx. Differentiating kx will, since we are differentiating with respect to x, differentiating x will give us 1 multiplied by k. So we are going to get k here. Then differentiating the whole thing, sine, gives us cos of whatever is here, kx. So now we are done. We compare whatever we get to the general equation. Well, we have a function sine kx here, an operator d dx acting on a function sine kx here gives us a constant and a cos kx. Because this is cos and this is sine, which they are not the same, this function here is not an eigenfunction. So sine kx is not an eigenfunction. Show whether the function e to the power kx is an eigenfunction. In this case, kx squared. On the operator d dx. So operator operating on the function f of x to give us a constant and the function back if it is an eigenfunction. So here we have d dx operating on e to the power kx squared, e to the power kx squared. Then what do we get? Differentiating exponential function. We are going to write whatever is here, e to the power kx squared. Then after that, we multiply everything by differential of this. So differentiating kx squared, since we are differentiating with respect to x and k is a constant, differentiating x squared gives us 2 multiplied by x to the power minus 1. So it gives us 2kx. So 2kx. So now we are done. We now compare to see whether the function e to the power kx squared is an eigenfunction. While we have an operator operating on the function, we have the function back here. Now let's see whether we have a constant. 2kx is not a constant because of x that is there. This term here is not a constant. We are differentiating with respect to x. So this term here should be constant. It shouldn't be, the variable that we are varying shouldn't be part of this term. So e to the power kx squared is not an eigenfunction. Let operator A equal partial derivative with respect to x and operator B equal negative I partial derivative with respect to x plus partial derivative with respect to y. Show that the function of f of x and y equal e to the power minus x plus y is an eigenfunction on operator A with an eigenvalue lambda equal -1. Is f of x and y an eigenfunction of B? If so, what is the eigenvalue? So this question is in twofold. Is in the first part is asking us to show the operator A is an eigenfunction on f of x and y with an eigenvalue of -1. And the second part is asking us to tell or show whether the operator B, f of x is an eigenfunction on operator B. If it's indeed an eigenfunction on operator B, then we should write out the value of the the eigenvalue. Let's proceed with part 1. Part 1, we are talking about operator A. So operator A operating on f of x and y should give us, let's say, lambda f of x and y. That is if it is an eigenfunction. But the question proved that it is an eigenfunction. We are to prove that indeed it is an eigenfunction. So operator A is partial derivative with respect to x. So partial derivative with respect to x, and the function f of x is e to the power negative x plus y. So e to the power negative x plus y. We are going to differentiate this partially with respect to x, which means we are not going to be much concerned on the variables y. So like the normal differentiation, we write the exponential term out. We just write it out as it is plus y. Then after that, we multiply the whole term by the derivative of the exponential power, which is this term right here. So differentiating minus x plus y with respect to x, we are only going to differentiate the x term leaving y. So if we differentiate x minus x, we are going to get -1 plus y. Since we are not concerned with y, we are differentiating with only x, the y term goes 0. So this term is basically going to be -1 because we don't have any x term attached to y, so it goes 0. So it means that we are going to multiply this whole term by -1. So let's simplify it further. D over dx e to the power minus x plus y equal -1 e to the power minus x plus y. So comparing this to the general equation, we have the operator a operating on the function e to the power minus x plus y, giving us the same minus e to the power minus x plus y, which is the function right here, with a constant -1 here. So we are done. This is what the question is asking us to do. It's true, f of x is an eigenfunction on the operator a with an eigenvalue of -1. So from here we are done. Let's look at the second part of the question. Is f of x and y an eigenfunction of on b? So let's say if it is so, then b operated on f of x and y. So give us a certain constant here. Let's call it c, and f of x and y again. So operator b is I partial derivative with respect to x. So I partial derivative with respect to x plus partial derivative with respect to y, multiplying the function f of x, which is e to the power minus x, e to the power minus x plus y. So e to the power minus x plus y. So what do we get from this? We have to expand the whole thing. So first of all, we are going to get I partial derivative with respect to x, multiplying e to the power minus x plus y, then plus partial derivative with respect to y, multiplying e to the power minus x plus y. No matter how the question is framed, you should just put your mind on the general formula. Then the rest will be your mathematical workings. But we shouldn't forget the minus sign here. The minus sign of I from the question. So there should be minus sign here. So now let's try evaluating this. Let's simplify it to we have minus I d dx e to the power minus x plus y plus d dy e to the power minus x plus y. So here we are differentiating this term with respect to x. So differentiating this term with respect to x, we just write the exponential function. Then after that, we multiply it by the derivative of its power. So differentiating minus x plus y gives us -1 plus 0. So -1 plus 0. Don't forget that we have I here. So -1 plus 0. We just multiply this time by -1, -1. But we do have minus j here, minus I here. So don't forget that. So now plus, we are going to differentiate this term with respect to y. So we write the exponential function. Then we now differentiate its power and multiply it here. So we are differentiating the power with respect to y. So differentiating with respect to y, if we differentiate y, it will give us 1. And this term will go to 0. So 1, multiplying this part by 1. So now let's simplify the whole expression. We have minus j multiplying minus I. We should give our positive I. We have minus I multiplying minus 1. We should give us minus I. Then e to the power minus x plus y, and then plus 1 multiplying by this is the same as writing it as e to the power minus x plus y. So now what do we do next? We are to see whether e to the power minus x plus y is an eigenfunction on the function f of x plus y. So we try to compress the whole thing in the idea of eigenfunctions. So now let's factor e to the power minus x plus y out. So if we bring e to the power minus x plus y out into bracket, we will have I and then plus 1. So this is the same as that, because if we expand the bracket, we will get the same expression here. So e to the power minus x plus y multiplied by I will give us I e to the power minus x plus y, plus e to the power minus x plus y multiplied by 1 will still give us this. So now that we are done, let's arrange it, because in an orderly manner, e to the power minus x plus y. So now let's go back and compare. Right now, we have solved all of this thing to be this. Evaluating this whole thing here gives us this. So this could equal minus I plus 1, then e to the power minus x plus y equal minus I d dx plus d dy multiplying e to the power minus x plus y. So now let's compare and see whether operator A is an eigenfunction on f of x and y. Okay, operator B. We have operator B here acting on the function to give us the function back here and a constant here. As far as we don't have x or y term here, this is a constant, right? So the function, f of x and y, is an eigenfunction on B. Therefore, f of x and y is an eigenfunction, is an eigenfunction on operator B with an eigenvalue, because we're asked to also state the eigenvalue, with an eigenvalue which is this here, eigenvalue of I plus 1. So that is it for this question. So in summary, once we hear an eigenfunction operator, try to recall this general formula. So an operator is said, a function is said to be an eigenfunction on a given operator if the operator acting on the function gives a constant and the same function back. Then we can call the function to be an eigenfunction on that operator. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.